Thank you very much, Richard.
Thank you. Hi, I'm Richard Terry, CTO at Wildfish, which is a London-based Python and Django consultancy, and I'll be talking about Python's syntactic sugar and how you can use it to make your code simpler, but also the trade-off that has for you when it comes to maintaining your code. These are not techniques which I would normally use in my day job because I don't want to inflict them on my colleagues, but I do think they have their place, and that's when I'm writing library code and trying to build a clean API for others to use. The Z of Python, for those who haven't read it, it's a list of guiding principles. It basically says, write clean code. The techniques that I'm going to talk about help you do that by shifting complexity away from what you're trying to write and making the code that's left behind simple and beautiful. But that comes at a cost, because the techniques themselves introduce complexity. To let you write the simple code, you're going to need to write something complex and ugly. And it introduces implicit actions, so magic which causes things to happen behind the scenes, and it can lead to unexpected side effects, and it can make things harder to debug when they go wrong. So wise developers often say, oh, you should never do that, and there are very good reasons why you shouldn't. But I think there are times when you should, because as I say, these techniques let you hide the complex, ugly code away from the people who you want to make things easy for. It is a trade-off about where you want the complexity to be in your code. And your challenge as an author is to decide whether the advantages outweigh the disadvantages. So, on to some of the techniques. Start with decorators. It's not a controversial topic at all. I don't think anybody would say don't use a decorator. But it is a good place to start. So for those who haven't used a decorator, a decorator is something, an @ sign before your function, and they are the easiest way to move boilerplate functionality out of a function, and they let you process and alter arguments as they go in, results when they come out, and they let you do things to the function themselves, like automatic registration, or you can perform introspection on it, those sort of things. Very briefly, a contrived example. So we have a function, and we want to ensure that the argument is a string. That bit is clear, and it would be fine if until we wanted sort of to do this 10 times, 20 times, because then we'd need to write those 2 lines out each time. And it starts to get messy, and it introduces the risk of variation, especially when you're doing a bit more than the 2 lines and it's getting more complicated. So one way to avoid that would be to move the validation out into a decorator. And that's nice and clean. It leaves nothing else cluttering the function up. It only contains the actual logic for writing to the screen, as the function describes. So it's really clear and easy to follow. But this already comes at a cost. So this is your decorator. For those who've written decorators before, it's nothing shocking, but you can already see that it's not as clear as it was last time. We've turned our 2 lines into 6, and this is a very contrived example, as I was saying. Things get a lot worse in the real world. So for a real world example, this is an echo server using Mara, a networking library I wrote. Mara uses decorators to register event handlers. So here we have a receive function. It receives an event object and then writes the data in the event object back to the same client, and this function is registered with the Mara server by using the listen decorator, which effectively just says listen for a receive event and then pass it into this function. It was about as simple and as clear as I figured you could make a networking library, but it does come at a cost. There's nearly 150 lines of code there, and there's no networking or anything in that. That's literally just what the decorator does to ensure that an event reaches the right function. And that one-line decorator obviously hiding a lot of complexity. So if something goes wrong in here, it's going to be pretty difficult for somebody who isn't familiar with Mara to figure out what's going on. It's difficult for me to figure it out. So by making the choice to simplify the API for other people, I've significantly raised the barrier to entry for any potential contributors. And I've made a bit of a job for myself. But I'm happy with that because my goal was to write a library which made networking easier. And I think that this achieves that. But decorators are generally considered okay. So let's get a little bit darker. Metaclasses. There's a bit of fear about this sometimes, but they're essentially just invisible decorators for your classes. The way it normally works is that you would define a base class at the bottom, so my class, and then it would use a custom metaclass, which is defined at the top. A Python class has an init method. That is what happens when your class is instantiated. And a metaclass has an init method as well. And that's what happens when your class is defined. So that means that you can manipulate the class attributes as the class is created. And that lets you do things like setting defaults, updating defaults, enforcing restrictions, like checking for required class attributes, performing type checking, things like that. And again, like we have with decorators, you can use it for introspection, or you can use it for registration. So here we want to automatically register a model. We want to automatically register a class with a registry. So here the registry is just a dict. And so what we're going to do is have a base class, registry base. That's not going to have any useful things in it, so we don't want it to end up in the registry. So we'll set abstract equals true. Now that means nothing to Python, there's no native meaning to that. But when it goes into our meta class, we can then pick up that attribute, say if the attribute, there's a little bit convoluted way of saying it, but if the class has abstract equals true set on it, then don't register it. We'll just return out of the init function. Otherwise, add it to the dict. So this is a pretty common pattern. I've used it myself in several different projects. And you'll frequently come across it in the wild without realising it. And a good example of this is in Django models. So obviously, this is very simplified. I've stripped out everything except what we're talking about. But this is essentially what you'll find in Django's base models. And this pattern works really well for Django because it needs to have a global registry of every model that's been defined so that it can create foreign keys and things like that. And it makes it really easy for the user to work with the model. As you can see at the bottom, when you're defining a model, you just subclass the model and it automatically gets registered. But there are different ways that you could have done that. You could have just registered it with a decorator, or you could have just made a function call. So you will find both of those in Django. They use them for template tags and the admin site, things like that. So why would you use a meta class over other options? Well, it saves you a line, basically. It's a little bit of less boilerplate, and it's one thing less that your users need to remember to do. So if they're so good, why don't you use them everywhere? Well, because they're too magical. Without knowing what we've just talked about, you look at that code and you have no idea how Django is going to find your model, how it's going to register it. And that's all right for the models, but it's a problem for template tags and for the admin site where you might want to have multiple template processors or multiple admin sites. You have no way of controlling how it gets registered. Meta classes exist essentially to hide explicit logic. Here, registration is completely implicit, and you just define a model and suddenly Django magically knows about it, which is why the Zen of Python discourages this sort of thing in the first place. Let's push on. Monkey patching. For those who haven't come across this before, monkey patching is basically changing code at runtime. The most common reason to do this is probably in tests, where you want to make a temporary change, stub something out. So here, we're going to be tricking anything that calls os.path that exists into thinking that that path exists. So you might want to do that outside in other areas of your project, so that your code works with somebody else's without you having to change their code, without having to get a pull request accepted for whatever reason. So all we're doing here is just overwriting a variable. When other code comes to look for it, instead of finding what it's expecting, it finds what we've told it instead, and we trick it to do what we want. But again, this introduces potential problems. So firstly, you have to be careful not to break other people's code, because you're changing their expectations. When somebody calls os.path.exists, they're expecting a boolean back, true if the file exists, false if it doesn't. As long as what you do on top of that doesn't break it, then you'll be okay. But with a more complicated function, more complicated return values, it becomes a lot more risky. So you've got to be more careful. The best way to defend against problems there is, of course, tests. If you write tests for the old function, tests for the new function, you can make sure that they all match up. But the second issue is that if something goes wrong, it does make it harder to debug. The original code has now been obscured. Your new code is now in the stat trace. And that can be a bit confusing for people who weren't expecting to find that. But as long as you're aware of the risks and you take care around them, monkey patching can be another powerful ally when trying to make your code easier to use. So, let's see how these come together in a real project. Tagguless is a tagging library I wrote for Django. It basically lets you categorize objects in a database by associating them with one or more tags. There were several tagging libraries out there already, but they used generic from keys, which are a Django-specific way to loosely relate objects in a database. And it works well for Django, but the databases don't understand how it works, so it means that generic from keys can be quite slow and difficult to work with. So one day I got fed up with them and decided I wanted to use a native many-to-many relationship. And I thought, how hard can it be? So I wrote Tagguless, which is both an easy-to-use tagging library and a perfect case study in how to build a package which is almost impossible to maintain. So, where to start? I wanted to be able to set categories by using either a list of tags, a list of strings, or a comma-separated string. So, to be able to process both of those, I was going to need a custom field. That's the obvious place to start. I also want it to be a many-to-many relationship, so it makes sense to subclass the many-to-many field. So there's my tag field. So far, so good. But many-to-many fields need a relationship to another model in the database. And to do that, we're going to need to explicitly define a tag model every time we want to use the tag field. The other tagging libraries don't do this. They get around that problem by using a generic from key, but I want to get away from that, so that's not going to work for me. Also, I don't want to have more boilerplate than the other libraries, because I'm trying to make this as easy to use as possible. So I figured, let's create a unique model automatically at runtime. It turns out that Python's really good at this, because the standard class syntax at the top is basically just syntactic sugar for a call to type at the bottom. As you can see, we've got the name of the class, the base classes for our class, and the attributes in a dict instead of a list. It's basically the same thing. The side effect of this, because we're still setting models.model as a base class, it means that it's going to use the same metaclass that we were looking at earlier, which means it's going to all get automatically registered with Django, and Django's going to think that it was there all along. So that's great. We can call type directly, generate the model automatically, but where do we do it? My first thought was to put it on the init function, but we need each field to have its own unique tag model, because each tag model name needs to be different, otherwise it'll end up in the same place in the database, which we don't necessarily want. It's going to have a unique but consistent name, so we can't just auto-increment because the order of things might go in the wrong order. So it needs to be based on the model that we're putting the tag field in, and the name of the tag field that we're putting on that model. But init won't have that information. We have to pass it in automatically, and I don't like boilerplate. So, metaclasses come to the rescue again. It turns out that because certain Django model fields need to know something about the model and about the field name that they're using, Django metaclass already has a way for us to get this information. If it doesn't, we could monkey patch the base class. We talk about that in a moment. But we don't have to worry about that yet, because the metaclass at the top, again, this is just a stripped down version of what Django does. The metaclass at the top will call the contributor class at the bottom, and you can see that now we've got the name of the class that we've added the field to, we've got the field name that it's being added to, so we can generate, on that line there, we can generate a unique name for our model. But this is what I mean when I say that making your code nice for your users comes at a cost to you. Because this was all just to save our users from typing out 2 lines of code to subclass our base tag model. And the deeper I got into Tagulous, and the more of this I tried to do, the worse things got. So if you want to see some entertaining monkey patching insanity, have a look through the source code. There are lots of things there, such as monkey patching class inheritance. Here we are injecting a new base class underneath our user's model. This allows us to override how the normal base class works. And by doing that, we can inject code which understands how the tag field works and trick anybody's code into thinking that it's built into Django. So, fair enough. There's also swapping the class of an instantiated object. Now, obviously, that's going to end badly if you're not careful. But it has the advantage over changing the base class that we're appearing ahead in the MRO, so we are going to be called before the original code, before the user's code rather, sorry, which means that we can process any data before it gets into their function, so that again, it looks like it's a natively supported field. And there's a lot more in there as well. I had to work around problems with Django serializers, the admin site, and what started out as a very simple idea, let's just use a many-to-many field, ended up being a very, very deep rabbit hole. And I've tried to mitigate these with test coverage, lots of comments and code, and even documentation for potential contributors. But there's no getting away from the fact that there's some pretty hairy stuff in there. That said, I find it useful in my projects, and other people seem to like it. So I think overall it was worth the effort, and it was kind of fun. But it is possible to take these things too far. And I can't finish this talk without giving you an example. Introducing my new Perl model. This brings the elegance of Perl's native regular expression syntax into your daily Python code. This works, and it is up on PyPI right now. It essentially monkey patches the Python interpreter to add Perl regular expression syntax to the language. It is, by any measure, an abomination. It's an exercise in what you definitely shouldn't do, even though Python lets you do it. It's full of horrors, such as injecting Python's regular expression module into every single imported file. It uses import hooks to pre-pass the source as it's imported, so that it can be rewritten into valid Python, if you can call it that, before the real interpreter sees it. And this lets us replace variables and rewrite entire lines of code on the fly, which is about as sensible as it sounds. Because the cost of introducing this syntactic sugar is obvious, what happens when we hit a problem? Well, an error will get raised in the code we've generated, and suddenly your error messages don't make any sense. At least not without an in-depth knowledge of how the module works. Now, I've got plans for this. All I need to do is write a global exception handler to pass this message, rewrite it so that it matches what they'd originally written. But that's probably a talk for another. That's probably a topic for another talk. So obviously, this is taking these ideas too far. But where is the line that I crossed? When should quite obvious. But when should you consider these techniques? As I've said repeatedly, these techniques come with a cost, and you shouldn't use them unless you're willing to pay the price. But in my opinion, there are times when it's worth it. So firstly, do it for your users. Library code you're releasing should be easy to use. And it's not necessarily a purely altruistic thing to do this, or even doing it on projects that you're going to release. Often, the person using this code is going to be you. So, by centralising your boilerplate stuff and hacks on all those things into a reusable library or a core module, you'll make the rest of your code easier to follow. And your colleagues will hate you. But, always bear in mind the trade-offs. It does make it harder for people new to the project to understand how it works, how to contribute, and it makes the code harder to follow and to debug. What you don't want to do is create a terrifying monster sat in the corner of your code that nobody ever wants to go near. Keep the hairy bits small and well-defined, ideally in self-contained code functions or modules called monkey patch or monkeypatch.py, that sort of thing. And leave plenty of comments all over the place to explain what you're doing and why you're doing it. And most of all, cover it with tests. Test your code, test the code you're going to call, test the code that calls your code, test third-party code that you don't think is related to it in any way, but it turns out that you end up getting a lot of issues coming into GitHub. Also, of course, if you've got lots of tests, then you can start making changes to it without having nightmares. Without tests, writing this sort of code, everything's lost. These techniques are definitely not for every project. Don't do them just because you can. But they show that with some effort up front, you can make your code, or your user's code, much cleaner and much easier to write and maintain. The question is, how far are you willing to go? So if you'd like to find out more, I've put some notes and links, I'll probably flesh it out over time as well, up at that link. I don't think we'll have time for questions, but I will be around for the rest of the conference, so do come and find me if you'd like to chat. Thank you for listening.